Okay, so actually, contrary to what John suggested, my presentation doesn't actually give any test data. In fact, what I'm going to discuss really is the product focus, and provide more context of what it is we're trying to achieve in High Record in terms of the technology we're developing and how it's going to be impactful in industrial decarbonisation. We're already working in developing this technology that we call CycloneCC, and it's our process intensified CO2 capture utilizing rotating packed beds. So I think the audience here is all pretty well informed about the challenge that we're facing and the need for us to be taking action in order to overcome these global challenges and the we're facing. It's well understood. Everyone knows what the challenge is, and there's really no kind of credible pathway without deploying CO2 capture to industrial facilities and the energy sector if we're going to meet these net zero targets. I think there's no disputing climate change. I think we see it in front of us today. One of the barriers to actually taking any action right now and has been used as an excuse is that the cost of CO2 capture technology is prohibitive, it's too expensive, and people are waiting for the cost curve to come down. So, but with conventional technology that's available, that doesn't appear to be anytime soon. So we need to do some disruptive technology development in order to kind of provide that technology that's going to make the economics feasible. And another thing that we understand from our interactions with the market and our customers is that more than 50% of the industrial facilities that are looking to deploy carbon capture technology just simply do not have the real estate, the space to retrofit a conventional CO2 capture plant. So one of the areas that we're addressing here now is how we can make our CO2 capture plants smaller and more accessible for the industries that are demanding it. I think here I just want to kind of, this, if we split it into two sides, I think the first two boxes represent where we are today as a company as a technology developer and leader in the CO2 capture space. We have 49 global references where our technology is operating, capturing CO2, separating it from industrial gas streams. And to date, we've captured over nearly 2.5 million tons of CO2. And then if you look at the second two boxes, this is focusing on what our kind of mission is in terms of what I've spoken about on the previous slide, in terms that we see the need to reduce the size of the equipment dramatically. So we're targeting 50% footprint reductions and aiming to bring down the equipment size, or realize that by bringing down the key equipment size by an order of magnitude. And ultimately, this is what we feel is going to be disruptive in the market. It's going to make the economics favorable, and we can make some progress in kind of realizing that cost curve reduction. We're one of the leaders in the technology space in terms of our patent portfolio as well. We've got over 100 active patent assets, 18 different patent families covering different aspects of CO2 capture technology, and in coverage in 30 countries as well. So we're, CO2 capture is a global technology and reflected in how we're kind of protecting our IP globally. So some of our key market focuses, and this is where we see the greatest demand from the customer base. In the energy sector, we see that some of the natural gas pipeline, midstream operations like compressor stations. There are a number of viable opportunities with these sort of oil and gas energy providers, downstream refineries and petrochemical facilities as well. And at the moment we have a project that's active with ADNOC in the Middle East, and I'm going to talk a bit more about that because it's the first demonstration of our CycloneCC technology at a industrial facility. So they're a key partner of ours. Another key partner is Chevron. They're actually one of our major investors in our Series C round. They led that round and invested $100 million in Carbon Clean to support our development of the technologies. They see they're a strategic investor who are also an end user, so they're really invested in kind of helping us develop the technology that they see as being the game changer that's going to help them decarbonize their assets, kind of in industrial power. Similarly, Cemex, another investor in Carbon Clean, we're working on projects with them to look at how we can decarbonize the cement industry. So, and that's very similar to one of the project partners in High Record. We're trying to decarbonize a wetland plant in Greece, Hellas. So very similar sort of flue gas types that we're testing, developing for this technology in particular. And then other kind of heavy industry, industrial emitters such as the steel sector as well. In the new energy space, it's quite interesting. I think the e-fuels market is something that is developing now. We're a member of the Liquid Wind Consortium, and I'm not sure if you're familiar with Liquid Wind or heard of them, but there's a series of flagship projects that are in development with Liquid Wind, where we are providing our conventional CO2 capture technology that we call CaptureX in order to capture biogenic sources of CO2. That CO2 is then reacted with blue hydrogen from wind energy, and then that produces e-methanol. So we're combining like biogenic CO2, blue hydrogen. There's a catalytic process to produce e-methanol, which then is used as a e-fuel to help decarbonize marine transportation. So it's renewable fuels, and really quite exciting projects to be involved in, as we see a number of plants in the pipeline. And then I think another area where our CycloneCC technology is kind of really applicable is in the maritime sector itself. So actually deploying carbon capture on ships to reduce emissions that way. So with maritime, there's a couple of different ways. You can do fuel switching to renewable e-fuels, or you can actually physically capture CO2 on board ships. And with the size and space reduction of CycloneCC and these modular technologies we're developing, it's a really good fit for the maritime sector. And we recently announced an MOU that we signed with Samsung to develop the technology in that space. So CycloneCC, as I've been saying, it's our modular process intensified CO2 capture technology. You can see the image on the left hand side. This is a 10 ton per day demonstration unit that's actively in operation right now in the Middle East at a ADNOC facility. So this was designed and built out in the Middle East as well. So it was 100% prefabricated in a workshop, much in the same approach that we're taking here in High Record. And we're planning on offering this technology to be able to scale up to round about, we feel somewhere in the region of 850 tons per day. So we should be able to offer industrial sites that have anywhere from 75 all the way up to about 850 tons per day decarbonization. through a series of product ranges that we're developing within that CycloneCC technology portfolio. The advantage here is that we're addressing the total cost of ownership. So total cost of ownership is essentially what the cost of the equipment means over the full operating life cycle of that equipment, taking into account the not just the capital expenditure, but that operating expenditure over the time. So with CycloneCC, we're really focusing on kind of minimizing OPEX, but then we've got other elements of our process which are helping to reduce the total cost of ownership through OPEX reductions. And the philosophy here is that this product is kind of standardized so that we can produce it en masse in the way that we've seen successfully the kind of cost curve reductions for other kind of renewable technologies. We see that's the way that you can bring the cost down here is through standardized units rather than doing bespoke, ad hoc design to order. We want this to be a standard unit that we can produce at large scale. So, and I've already mentioned that another natural fit to this is putting this on board marine transportation and applying direct point source capture whilst the ship is in motion because of the compact nature, the reduced size, and also the kind of the advantage you have with a kind of a smaller compact system is that you're against kind of conventional towers is less sloshing and reactivity towards the kind of motion of the ocean as well. So what does the CycloneCC process look like? I mean, we've seen amine plant flow sheet a couple of times already this morning, and this is a slightly different take on this. So CycloneCC is essentially going to be columnless CO2 capture. So we've seen the flow sheet that Sakis showed and John showed as well. This is analogous, but everything that would normally be a process operation involving a static pad bed column is now replaced with a rotating pad bed. So we can take our flue gas from an industrial process and we can apply it, pass it through a pre-treatment section where you're cooling down the flue gas and also removing impurities such as NOx and SOx. So you've got that pre-treatment of the flue gas. Cooled flue gas would go into a first stage of an absorber, and John showed a photograph of the high record RPBs as well, so showing these two RPB stages, and that allows you to include interstage cooling so that you can optimize your CO2 absorption, cooling the solvent during that CO2 gas contact in order to optimize the temperature regime through to a second stage of absorption before the treated flue gas then would go into a water wash, which again can be provided as an RPB to provide that size reduction. We've actually worked with John. One of the last things that we were doing in our Artemis project was generating test data for our 1 ton per day RPB absorber, both in the application of a pre-treatment section and a water wash section. So we've got data. We know that we can operate this RPB in this way, and now we're in the process of kind of scaling this up so that it can be incorporated into our product. And then on going back to the solvent loop, as we've seen already as well with John's presentation, you can use RPBs for generation either with an integrated reboiler as John showed for the ISR, or as a separate reboiler in an analogous system to a conventional plant. So this is the vision of what CycloneCC looks like, what modular CO2 capture technology, columnless CO2 capture looks like. Our process uses CDR Max, as has been described already by Sakis. It's what we're using in the High Record project. It's a high-performance amine-based solvent with improved corrosion properties, which we're validating within the HyRecord project, lower rates of degradation, lower energy demand for regeneration, and overall that gives you an increased solvent lifetime so that you can save on makeup costs. Going into a bit more detail, I covered some of these KPIs, but also we've got quite a lot of test data. We've demonstrated APBS CDR max at TCM in Norway, which is the world's largest CO2 capture demonstration facility. We showed that we got class-leading emission data, so solvent emissions in kind of double-digit ppb levels. Energy demand reductions anywhere between 10 to 25% relative to MEA, and I've already kind of mentioned about the solvent lifetime. So this is one of the OPEX drivers within the process and how we can bring down that cost to capture relative to the current state of the art of columns and MEA. I wanted to touch on the development, maybe not in as much detail as John has, but our involvement with RPB started in about 2015, and we wrote a proposal, got a very modest amount of funding from the UK government to kind of build our first RPB to test our solvent with, which was built by John in Newcastle, and we tested our solvent and MEA as John's alluded to already, because we felt that there was some reports in the literature about RPB for CO2 capture, but this hadn't really been performed in the right way. We felt that some of the test conditions weren't reflective of real kind of applications. So we wanted to kind of build this ourselves, get an idea about what generating, how we could generate test data with our solvent, prove that it would work. And then in 2018, we got funding again from the UK government, slightly more this time, and that was in order to kind of scale up and come out of the lab to the pilot plant. And this was the Artemis project that John has already mentioned. And it was in 2020 that we actually got our pilot plant up and running at Outre Babcock in Glasgow. They already had a facility that was column plants with a capacity of 1 ton per day. And we took our new shiny RPB absorber and tied it in using the remaining balance of plant. So we're just swapping out the conventional column for this RPB, and we were able to demonstrate that with the RPB, we can realize a size reduction of 10 times compared to the conventional column with MEA using our solvent. I haven't got the data, but we did achieve capture rates as high as 95% using CDR max. And then really the learnings from this enabled us to design and scale up further to this 10 ton per day demonstration unit that we see here, that's in operation since the summer of 2024. And I'm very pleased to announce that last night, an iChemie award ceremony, our team was recognised and they won 2 awards in the 2 categories that the Artemis project was entered for. And this is the team kind of relaxing after winning. These guys were the guys that were on the ground operating that pilot plant, and they really deserve the recognition that they've got for this. I think John's spoken a bit using some kind of static images about how the RPB gas and liquid flows work. We've produced this animation of that test facility that shows the gas liquid flow through the RPB, kind of really lifting the lid. So you can see that we've got our rotating packing there. The liquid's introduced at the inner annulus, sprayed onto the packing, and then with that rotational motion, the centrifugal force that's applied to the solvent, the solvent travels radially outward from the inner edge of the packing to the outer edge. And then you can see coming from the outer edge, we have our flue gas being supplied. So that's represented by that kind of purple fluid. So that's traveling from the outer edge to the inner edge, so counter current contact between the gas and the liquid. And we have that selective absorption of CO2 into the solvent that you would expect from a conventional packed bed as well. So this animation is quite nice in showing those flows rather than just a black box. So as I've already mentioned, we validated and achieved a 10 times size reduction in terms of the packing volume with this RPB, and that actually was even with it being undersized, as John's mentioned as well. So we've also tested not only the ExpoMet packing, we tested the packing from Mons, and we've also tested a metal foam packing. So we've done quite a rigorous evaluation of different packing types, and yeah, the Mons packing is the one that works the best. So yeah, our 10 ton per day unit is in operation. It started in the summer. It's actually the date here needs to be extended because it's going to be running for another few more weeks. But the Fertiglobe are a wholly owned subsidiary of ADNOC, and the industrial site is a fertilizer plant. So we're capturing CO2 from a natural gas boiler. That CO2 that is captured is then also being reused on site to produce urea. I've got a video here that shows the kind of modular nature of the CycloneCC systems and how easily it can be installed. So what we're doing is, this is a time-lapse video showing the installation of the individual modules. So this is only 4 days it took us to install. Yeah, that's basically 4 days of craning in our modules so that the modules can be shipped on the back of a lorry, brought to site, offloaded with a crane, and fit into place. So it's a bit like Lego blocks in terms of the connectivity and the ease of installation. So yeah, that's, I don't need to see that again. But yeah. What you may have noticed in that video is that we still have some columns in that unit. So we haven't, in our first demonstration unit, we haven't converted the pre-treatment section or the water wash to an RPB. So for us at this stage, the main thing was to demonstrate the main CO2 absorption and desorption process could be achieved using RPBs. But the vision, so the version 2.0 of CycloneCC that we have recently announced is the completely columnless plants. And this is what we expect the system to look like. And you can see that the big two RPBs in the middle here are the 2 stages of absorber. On the right hand side, yeah, maybe if I use the pointer. Here is our kind of gas inlet on our pre-treatment section. Got 2 stages of absorption, and then a water wash RPB here, and then our RPB regenerator is up on this top deck. So this series that we're calling C1 is nominally 100 tons per day CO2 capture, and we can significantly reduce our unit footprint, so up to 50% compared to a conventional plant. And you can see from the dimensions shown here, I think this is kind of the reality of it, that we can really reduce the footprint and the overall equipment size. So yeah, for a 100 ton per day plant with a footprint of around 15 by 20 meters, this is what we're trying to achieve. The elements of minimizing the costs come from the capex reduction of producing RPBs, our existing like market leading solvent, although we are also looking at developing a new solvent as well. We don't want to stand still in terms of our solvent technology. We're looking at new chemistries, novel chemistries that can perhaps give us a further edge. And then one of the other things that we're incorporating into our plant design to optimize operations is the use of digital technology like machine learning and AI, so that we can optimize fleets of remote carbon capture plants to gain energy savings, where we we're generating lots of data that can be analysed to show where the optimization potential is with those plants. Here's just a kind of a brief overview of where our projects are right now. We've got 44 biogas plants about 42 in operation right now in Europe, where we're upgrading biomethane into biogas into biomethane. We've got our CycloneCC demonstration in the Middle East, and then we've got a number of more semi-modular plants using conventional columns in India and Japan. Here's a list of kind of key partners who we're working with in order to kind of develop, build, and demonstrate the technology. And I've already kind of mentioned a number of our key investors as well, who have kind of share our vision and enthusiasm for developing this technology. Where do we see the potential for deploying this? I think the opportunity is vast. We've done a lot of work mapping out these industrial facilities that we want to decarbonize or help to decarbonize, and there's plenty of them. So there's lots of CO2 to capture. There's lots of facilities around the world. I think, reinforcing what I was saying at the beginning, we're trying to solve a global problem, and in order to do that, we think big, but we build small. So that's everything that I have for you.